So we're just gonna. I'm not necessarily going to try to motivate this. Let's just have fun together, shall we? And just explore this, or my notion of fun. May not be yours. If you want to hear about databases, feel free to leave at any time. You can do those universally too. But that's a different talk. Disclaimer: this talk contains lies. And some of the lies in this talk, not all of them, this is more lies than any single paper could correct, but this paper will help to correct some of them because we're going to be doing the stuff where we talk about category theory in Haskell, but the correspondence isn't exactly what one would hope, and so we're going to gloss over a lot as we go to sort of fit it in 45 minutes and keep it light and fun for some definition. This talk arose because I was trying to understand category theory, and universal properties come up a lot, and people say category theory is all about universal properties. And you start to read about universal properties, and you go to Wikipedia, and they say, the best way to understand universal properties is category theory. So I said, okay, well, but what is category theory? Well, it's a way of understanding universal properties. Thank you very much. I started to figure out, is this thing going? Yeah, so let's just talk about what properties are. Maybe, there's many definitions of properties. Some involve ownership. This is a mathematical definition that'll help us in this talk. So take some notion of a mathematical object, which is, again, an ill-defined term, but it's an object that we're going to treat mathematically, and take some notion of something you can do with it, and then we're going to call that a property. And so you can say a wheelbarrow is a mathematical object, can have a color, and that means we have a function, wheelbarrow to color, and therefore color is a property of wheelbarrows, or something of the sort. And we need some definition like that so we can then figure out what the word universal is going to do. All right, but first let's talk about what a category is, or a property is in a category. For the purposes of this talk, right, a category is a bunch of dots and some lines between them, and the lines have little arrows on the end. And every dot implicitly has a special identity arrow to itself that we're not going to bother to draw. And if you have an arrow that goes from here to here and an arrow that goes from here to here, they compose and they induce an arrow that goes from here all the way to there, just like function composition. But other than that, arrows are not necessarily functions. And if you think of arrows as in general functions, then you're going to be in a lot of trouble because in a lot of interesting categories, arrows look nothing like functions. Can be in like a preorder, and an arrow can represent is less than or equal to. You can be in the category of matrices, which we'll get to later, where the dots represent n by n matrices for each value of n, and the arrows will be m by n matrices that take matrices of m to matrices of n, and you do that by multiplication. And so that's a class of functions, but it's not all of them on matrices. So that's how we're going to treat that. So a property categorically is going to be an arrow, or maybe a collection of arrows, from one dot to some other dots. A universal property is going to be still something you can do to something else, but something that somehow encompasses everything you can do to that thing. So it's going to be sort of universal with regards to that object. It's going to be the property of that object that tells you everything about it. And so an example that we see in Haskell is if you define the function if prime, right, that takes a bool, and we write if as a function, and then if it's true, it gives you the first argument. If it's false, it gives you the second. You can think of this as the universal property of a bool, because everything that you can do with a Boolean is encompassed in the fact that if you give it two arguments, it'll pick either the true or the false one, being the first or the second in some sense. So are we sort of comfortable with that as a notion? Feel free to say I'm not comfortable at any time, and we'll talk about it more slowly. We're going to not talk about what is and isn't up to ISO. That would make this talk twice as long. So let's not do that. This captures the essence of bool without direct reference to bool. I like homotopy theory, so up to ISO doesn't really come into it. So what is a universal property categorically? So, okay, now we're going to have to introduce a second concept, which is now you have not just one category, but two categories. One has red dots, one has green dots, or aquamarine dots. There's a line between them. What do we do when we have two categories? Well, we can take functors between them. So we said a functor is a bunch of dots and arrows, and they have identities, and they have composition, and things work as one would hope. A functor is a way to take dots in one category to dots in another, such that you also take all the induced arrows in a way that preserves those identities and composition. Right now we don't have a functor because we're not taking those dots anywhere yet. So that's not yet a universal property category. There we go. We call this a diagram. And we've got a category on the top that's typically small. Here it's got 2 dots. And we're taking it to a category on the bottom. And so we've chosen where each of those dots goes. We haven't drawn any lines between the guys on the top, so we don't have to pick where any of the lines go on the bottom. So that's pretty easy. That's a functor. It's between 2 discrete categories. It's not much going on there. That's good. Oh, now we've got a cocone. Okay. Oh yes, I should mention this talk is going to be about colimits, which we'll get to briefly. If you want it to be about limits, get the video when it comes out. Watch it with your monitor turned upside down. So a cocone is a cone that goes downwards. It's an ice cream cone. A normal cone is a traffic cone. We're only going to talk about ice cream cones. So here we've got the same diagram as before, but now we've added another dot in our category at the bottom that was lying around, and we said, for all the ways that we go to all the different dots, we're also going to induce a morphism to this one special dot, sort of the apex or the bottom of the cone or cocone, as it were. And if it was a cone, of course, the arrows would be going the other direction. Now we have the colimit. So we ramp up fast here. Again, stop me or tell me to go back or slowly or ask me what the heck I'm doing or to make it more concrete at any point. So now we got very fancy very quickly, right? You were with me on the dots, you were with me on the lines, and now what's going on here? And I actually don't know I haven't really timed this talk, so you'll have to forgive me here. Let me find there we go. I can at least keep track of my time. A colimit is a universal cocone. What makes it universal? So we've got a bunch of cones here. Here's a cone, right? Dots, lines. It's going to be a universal cocone when that special guy that we've made look sort of nuclear up there, because if you go to him, then you can factor through that to get to any of your other cones. And that's why those lines are dotted, is we say that they're sort of induced. And then when you have a universal cocone, it comes with all those lines for all possible other cones that one can have. It was a very abstract definition. Why am I showing you all this? What does this have to do with Haskell? I don't know. Yes? We're going to get there very quickly. So that I promise it will. That's why we're starting just because I want everything to be as general as possible. So therefore, there are no examples, and it makes no sense. Now we'll give you examples. So we say if there's n discrete objects, we get an n-ary coproduct, aka an either. And if there's 0 discrete objects, we get an initial object, which is void. So this example of a diagram I gave you is a discrete category with 2 objects at the top. So and now what it does is then we pick a particular set of 2 objects that are pointed to by those 2 objects at the top. So if, as we'll do often in this talk, we pretend that the category on the bottom is the category, the so-called category Hask, where objects, dots represent types, and arrows represent functions of type, left dot, arrow, right dot, right? And so that can be int, and this can be bool on the other side, right? You buy that? So the one dot is int, one dot is bool here. And then we've got some universal object, and we have functions int to whatever that type is, and bool to whatever that type is. Now, what happens? We want to say we want to have a universal thing, such that if I start with an int, and then I go to any other thing, and I can also start with a bool and go to any other thing, then I can go to this guy in the middle, and that captures exactly that I could have started with an int and gotten there, or started with a bool and gotten there. What is that type? That type is either left, right? Do you see that? That this diagram corresponds to what one can do with either, in some sense? We're going to show you some code later that will make that more precise. But that's what's going on here, is that this diagram, and I've left around the extra dots just to make clear that the diagram is not the only thing in the category, but this diagram corresponds to the either type in Haskell, or generally what we would call a coproduct. Yeah? The radioactive thing is the either. And the whole point is, if I can take an int to a string by show and a bool to a string by show, then one of those dots at the bottom might be string. And then I can take an int or a string, by those blue morphisms to either bool string. And then I could say, well, if it's left, show it, or if it's right, show it, right, as show bool or show int. And those are both ways to get to string. So all the ways that I can either factor this guy or that guy into the same type can be factored through putting them into the left or the right side of an either pair and then projecting them back out into that type. And that's what this captures. So that's a coproduct. Now, the blue dots are what we call, they're part of the diagram. So they're what indexes this entire thing. So imagine I had a third blue dot. That would be a three-way either, right? Because that third blue dot would pick out a third object, which would get added over here, and that would also point into the cone. What happens if I only have one dot? Well, that's really the identity functor, right? That doesn't do anything. It just, you pick out an object and get down to another object. But now, that's why I said, what if we have 0 dots up there? It's crazy, right? That's what happens in this case. We've taken away all the dots. So we're left back with induced morphisms, but we don't have any dots, so we don't have any way to get to those. So we need a unique way to get to any type in Haskell, starting with no types. What is the type that can get to any type in Haskell starting with no types? It's the void type, right? It's for all AA, or this is how we tend to write it, is new type void equals void void, so it's a fixed point. You can't ever get to the bottom. And it has one function on it, absurd. For all A, void arrow A. You just can't evaluate it very well. But you can write this. It's in the void library on Hackage. When we ran the Hackage statistics, a lot of people depend on this library because it's easy to write instances for. So many, because you can use absurd. And if you want to write any particular instance, I'll give you one guess how to write it. So that's what happens as we go down from, you know, a 2-object coproduct to a 3-object coproduct down to 0. You get back to void. And you can sort of view void as the unit object if you treat either as sort of a monoid. Because, right, if I have either void A, that's the same thing as just having an A. All right, moving on. Here's a more interesting colimit. This one you don't really do in Haskell well, and it was hard for me to come up with good examples of, but it's a co-equalizer. So we've added some morphisms. We've got 2 objects, and they have parallel morphisms between them. And that comes down to having 2 types in Haskell, for example, and we have 2 ways to get from the first to the second type. And then this guy here is going to be a type so that if you come through the top way or through the bottom way, then here you really can't tell it apart. And if you were in a richer system or if you're in a set theory, you can make sense of this. In Haskell directly, it doesn't really do much. And so this is actually how one would normally draw the diagram. We can get rid of that extra arrow, and then that's the co-equalizer, is this morphism and this guy. And then for any other guy you can come down to here, you can factor through that.
Why do we need 2 arrows?
Because what the co-equalizer is it's constructed by the 2 arrows. Those 2 arrows might be different, right? They can be 2 different functions that do different things. And the co-equalizer sort of detects where they coincide. And that's what this is about, is because now it all has to factor through that other piece. This is very vague, and like I said, these are some of the weirder ones to get a handle of, because you can't really just write them as Haskell types. But in set theory, they work. So pretend that we have objects as sets, and morphisms are set theoretic functions now, right? Which you can think of as, you know, pairs for every object in the first set of, you know, the object in the second set it maps to. So you can think of them as a lookup table. And now co-equalizers are quotients, because they're ways of identifying stuff. So if you have f and g of type A to B, then the co-equalizer of f and g, and this is a lie, but it's a way to think about it, is if f of x is the same as g of x, so in the places where the 2 functions land in the same place, given the same input, then it's whatever that place is. They agree. If f of x does not equal g of x, then you have to create a special object that makes them agree. And here I'm just going to do that by the pair f of x comma g of x. That's not really exactly right, but that's an intuition for you've created a new object, a new type, a new set that sort of, when they coincide, it captures the thing they actually were. When they don't coincide, it's equalized them or co-equalized them so that they would have coincided. And that you've gotten rid of the places where they differ in some sense. Now, if you know much linear algebra, I don't, but I still came up with this example, but with help from Saunders McLean. Take the category of matrices that I mentioned, and objects are given by, you know, sort of n by n matrices, and the n by m matrices map between them by multiplication, and they compose nicely. It's a nice category. Co-equalizer of M and what we call the zeromorphism that sends everything to 0 is, if you know enough linear algebra, what they call the co-kernel or the left null space. Alternately, it's the x such that x times your matrix equals 0. And if you think about what that means in matrix terms, in terms of linear algebra, right, you're really solving an equation when you do this, right? You're sort of finding the places that, that nullify the system of linear equations. And so you can think of a no co-equalizer there as finding the solution to the question of how do I nullify these things. And that's one reason that it's not so easy to write with Haskell types, is it actually involves calculating on the concrete content of these functions that you're co-equalizing. But they do come up in interesting ways. Phil Freeman has a blog post here that, when these slides go on, you can go to that, and he says, what if Haskell did have equalizers and co-equalizers? And he explains it much better than I'm going to here. Now here's, if you know topology, another way to look at a co-equalizer that I find helpful. On the left-hand side, we have a dot. On the right-hand side, we have a line. We have two ways to take a dot to a line. We either put it on the left-hand side of the line or the right-hand side of the line, right? Now, if we co-equalize that, what's happened? We've tied together the left-hand and the right-hand side of the line. We've got a loop. And so the co-equalizer in the category of topological spaces of these two morphisms, the left and right-hand sides of a line, is a circle. And that's one way to generate the circle. So you can see the fact that we've identified the dots doesn't mean that we've gotten rid of the line between them. Right? It hasn't just collapsed them. It sort of captured that. And here we go. Now, here's a co-equalizer you can do in Haskell. I just learned this the other day. It's really neat. We're going to take two arrows again, but now they're going to be but we're going to identify the two objects on the top to the same object. So we're going to sort of contract this thing, right? And we're going to pull those two blue points on the top together. And we're going to say one of those arrows is the constant arrow, and the other arrow is going to be something that actually is interesting. So the constant arrow is the one that factors through 0. So there we are, two arrows on the top. We come down, we've got an object in Haskell. It's got two ways to go to itself, one of which is sort of constant, right? The const function, const x. And what goes there? What happens when we take this guy down to Haskell? And Freyd figured this out. That's natural numbers. The constant arrow is 0, and the other loop is successor. So if you take the co-equalizer of this guy, you get natural numbers. And piano numbers. And that's very interesting. And if you don't believe me, I hope you will shortly. First, I'm going to show you this guy. We don't really have these in Haskell either, but it's important because I want to show you the zoo. This is, if you have two dots and then one dot points to both the others, you call that a span. And if you take the co-limit of a span, you get what's called a push-out. And a push-out sort of combines the properties of co-equalizers and of coproducts in some sense. I'm not going to talk about that much, but I wanted to make sure it was there because we've got a result about it. If you have coproducts, so that should be co-equalizers, then you have push-outs. In fact, you can induce it. If you have push-outs and initial objects, you can derive coproducts and co-equalizers both from that. And if you have either of those conditions, you have what they call are all finite colimits, i.e. you're co-complete. So out of these, out of this tiny zoo I've given you, you can assemble them together and construct all of other possible diagrams from all other possible categories, finitely so, and then you've got all finite colimits. So that's why I went over all these guys, to show that. Now, I'm going to prove to you that this works in Haskell. So let's translate this all to Haskell types. Here we go. That's our either diagram, right? Now, we're going to put that into Haskell. So we're going to say the cone over the two for A, B, and T is going to be the morphism A to some type and B to some type. So it's the left and right-hand sides arrows coming in like that, right? And that's the cone, for any arbitrary cone. Now, we can take the colimit of that. How is that? That's the universal one. So that's just the arrow that can go from any particular cone over a type to that type. So we just say for all t, ft arrow t. So I take colim of f is just the thing that, for you give it something of kind star arrow star, and it just gives you that. And then we've given it a particular thing of cone over 2, which, if you apply the a and b, you get star arrow star. And now we take colim of cone over 2, of two types A and B, and that's either A and B, actually and precisely in runnable Haskell code. And similarly, data cone over 0, where you don't give it any arguments, is actually and precisely void in real Haskell code. And you can write code that takes these guys back and forth to each other and witnesses these isomorphisms, as we have done here. This sends either to that other type that we've written, our fancy either, and this sends it back, and you can also send it back the other way. And in fact, if you look at this, you can look at A arrow C, arrow B, arrow C, arrow C, and you recognize our friend, either, right, from data.either, which is what they call the eliminator for the either type, right? So, and it just says, if you tell me how to take the left-hand side or the right-hand side to a C, I can take you to a C. And the eliminator for either is the universal property for either. And we can now exhibit that colim of cone over 2 has the exact same function that's derivable from it. So it has the same universal property. And that, in fact, if you don't need to work the isomorphism through by hand if you witness that, because it's a theorem of category theory that if two objects have the same universal property, they're the same thing up to unique isomorphism. So that's why you should believe me, is you can run all of this. And so what's a really strange intuition about why this is even possible? Right? How does that for all let us do this? So again, this is an interesting lie here. So look at functions lambda x arrow x. You can have a lot of types, right? It can be typed int to int, it can be typed double to double, unit to unit, string to string. Now, if it's int to int or double to double, both of them are in a sense subtypes of num A arrow A, right? So you've got a little relationship there. If we were in liquid Haskell, so that we had refinement subtyping, we could say that even to even is a subtype of int to int. So arrows indicate the subtype relationship. What do we have now? We got a bunch of things in red and black arrows between them, just like on all the previous slides. What do we do when we have things in red and black arrows between them? I only told you one thing we can do. We can take colimits of them. There you go. There's a sense in which the most general unifier in a Hindley-Miller system can be thought of as, putting together this information. And that is a terrible lie as to why, when you do for all A, that's a way of sort of capturing a co-limitingness, or when you do exists a limitingness, I suppose. But that's something to think about, that all of these things are in a sense about tops and bottoms of lattices, just like type systems are. And that's why we can capture some of these properties in types, so not all of them. So universally quantified types are initial types in some sense. So I showed you the NAT one, and you looked at me and said, that doesn't work. So it works. I did this in Haskell. I wrote cone over loop. And it's the same thing as cone over 2 or something, but here we have a T arrow T and a T, right? We take the colim of cone over loop, and we can write, of course I should have positive integers here, not ints. Try to give it a negative integer, it won't work. And we've exhibited the isomorphism between, we've taken that diagram, we've turned it into code. We can look at the code, we can write the isomorphism. That sends integers to this weird colimit encoding of natural numbers and back and forth. And you can observe that, when you have the 0 in the successor function, and this corresponds to a fold over the pianos, right? You just tell me what to do with the 0 and what to do with the successors, and I can, that's induction that I can tell you what to do with any inhabitant of this, because I can keep applying these guys. So that's fun. Going a bit faster than I planned. I hope I'm not going too fast. I don't know. So now we get this metaphor that I don't want to expand on further because I can't do it precisely. But you can really see that we have colimits, initial algebras, what we learned as church encodings, right? Sort of, when you can build everything out of lambda, are all sort of very related ideas. And this gets to the idea that data and functions are very related ideas, because here we can look at pieces of data by their eliminators or their universal properties as just all the things you can do with those pieces of data. And you can go back and forth between the function of all the ways you can act on something and the concrete representation you get your hands on. And you've really got the same thing. So then I was really happy when I figured this out. We do the same thing we did with naturals by that result of Frades. And now we just index it by some arbitrary type A. So now instead of having just one morphism for successor, we have many morphisms for all the different objects of type A. So you get a lot of lines between those dots in itself up in our indexing category. You get a lot of lines down there. And now you get a list A. And again, this works. And we can write the isomorphism from list and to list. And if you're familiar with fold build fusion and all our friends like that and all that literature, you can see that from list and to list are the ways that you go between sort of folds of lists and lists in what should be actually a very comfortable way, right? That a list is universally represented by its fold. And then you can apply that fold to cons and the empty list and come back to where you started. And the fun thing is we got there just by drawing a bunch of squiggles up on the top there. And then we could turn that into real Haskell code. So it's something we knew, but maybe it's a new way to know the old thing. Now this is another old result that is bringing us through this portion of the talk. Here, if you have sufficient conditions and you have a whole bunch of dots on the top, and they just go on forever and ever, up to some notion of infinity. And here, what we map that to are the types void, then f of void, where f is, some, f of a, right, some sort of functor, and f of void, and f of f of f of f of void, and all the way on. And I've only shown you one thing to do with these diagrams. We take co-limits of them. We only know one trick. And so here we do it again, and those guys are in light gray because they're all sort of induced by the properties of the diagram to begin with. And so that's our cone, and we want to take the co-limit of that cone. It's going to look like that, right? We've got our nuclear guy. And so for any guy down here, if you can go down directly from anywhere in that chain, or you can go down via him, everything has to factor through that, as we say, right? So if you go here, you don't lose any information relative to anywhere else you can go. That's what's happening here. Then what is he going to be? What is that nuclear guy? That's the fixed point of a functor. And that's a result of Atomic. And there's many conditions that I'm not going to enumerate for that to work. That doesn't work in all categories. But it works in the only one we care about, right, which is the fake category of Haskell. So the co-limit of the chain induced by iteration of f is the initial f algebra. And this brings us to the whole theory of initial algebra semantics, which we're not really going to get into, but here's a way you can start off approaching it by drawing some dots and lines. So I promised I was going to talk about real code here. So I have a couple of stupid examples that should make this maybe so much more concrete you won't see what it had to do with the diagrams, but we're going to try. So an example of something where Yaron likes to talk about making data types that make illegal values unrepresentable or something. So we have a general problem that we like to think about as functional programmers, which is we want data types that can represent all the states we want and none of the states we don't for some definition. So they sort of want to snugly cover the space of what we're interested in. And the question is, how do you get to that? And one way to think of that is, again, think of all the things that you want as sort of a lattice, right? And you draw like which things that you want are more general than which other things do you want. And you draw lines between them, which things include which others, and you want to say, well, let me take the co-limit of this lattice. Let me sort of take the element on this lattice that encompasses all that stuff and nothing but. So here's an example of where that sort of thing tends to come up in the real world, is if you have date recurrence rules and you want to say on the third Wednesday of every month, or on the first and third Wednesday, or on the 17th, except if it's a holiday, in which case it's the 18th, or if it's a weekend, then bump it again. And one can have very complicated rules, and they can apply to things like calendar appointments, meeting schedules, batch procedures, nightly reports, bond payment schedules have day count conventions. And one wants to represent these sorts of things in computer programs in the employable world. So we might sort of talk about, well, gosh, let me give you a data type to represent these rules. Well, it's daily or it's weekly, and then I'm going to give you, Monday 1 to 7 is like, out of one of those 7 days of the week, or it's monthly absolute, except what if it's a month that doesn't have a 31? How do I capture that? Maybe it's monthly relative, like the day of the week relative to which week of the month, or maybe it's twice a month, and so I'm going to join two schedules, and we can keep going and going, right? And what what's something else we could do? Well, then we say, well, whatever we do, we're eventually going to have to come up with something that says, if it happened one day, what's the next day it's going to happen? You know, the interpretation of our schedule. Interp schedule is, you know, sched today. Now, we might say, well, gosh, that's not very good because we don't want to have something will happen next before when it just happened. We want sort of a, you know, monotone function in time. Right? You can't schedule things in the past. So instead of day to day, we'll say day to nat, where that's the difference, so that we've ruled out going back in time. So now what have we said? Well, a general schedule is not just it is just what happens when we interpret a schedule. It's the schedule under the action function. Right? In a sense, the universal thing about a schedule is it can send a day to a natural. Except maybe that's not good enough. Because, well, what if it only happens 4 times and then never again, right? Maybe it cuts off. So we'll send a day to maybe a natural, or maybe it's done and there's no more naturals. And then maybe another general schedule because, you know, the next natural, you know, maybe will be -1 or something, right? Because you want one less chance for it to happen. So now we've built that out a bit more, something like that. Maybe that's not good enough, but that's what we had. Now, why does it need to be a day? It can really be sort of anything, all right? You know, so there we go. We've abstracted out the day because that's not really doing anything. And now, as I said, but we apply some of this universal nonsense on prior pages, and we result with that's the same thing as that. And maybe right, that a day, right? If you give me a day, a schedule is something that you give me a day or a day-like thing, and I give you a list of the naturals of all the future intervals, you know, between which the rest of the things will continue until they run out. And that's a potentially infinite list. Now, you could probably have gotten there without going through any of what I did and just, you know, thought about it hard and came up with that. That's how I came up with that, though. So to each their own. So I think it is useful to think with. And I'll show you another example that actually happened in the real world where people collectively figured out something by sort of noticing how this stuff fits together. Maybe not in this exact way. So that's a universal schedule of some notion. And yes? I didn't get to it directly by taking Colim on GenSched. You look at enough of these things, you notice. You probably could do it more formally. But what happens is you get the intuitions and then you sort of see what's going on, in a sense. I actually haven't tried to take Colim on that. This is more of a general point about how one could apply these principles in practice. Now, Clojure came up with these guys called transducers in late 2014. Has anyone heard of transducers? There's a lot of blog traffic and mailing list traffic about these guys, and you know, they're the ones I'm talking about, of course, the ones that don't do mutation under the hood. So, you know, we were told these are not the real transducers, which are untypable supposedly because they do things that shouldn't be typed. So people said, well, what are these transducers that he's talking about and how can we understand them? Well, I know what we'll do. We're Haskellers, we'll give them types. And so he started with these guys called reducers. And a reducer says, you know, you can keep feeding, it has a Z, which is its state, and you keep feeding it A's and it keeps sort of bumping the state by the A's that you've been feeding it. And so this is what Rich Hickey had initially. He said, now we're going to transduce these reducers, and that's my great innovation. And you know, and he added all the stuff to the library and sort of showed all the things you could do by having reducer transformers, which he called transducers. And people said, well, if I turn this into Haskell and I ignore the mutation, it sort of looks like that. For all Z, A to Z to Z to B to Z to Z, right? It takes the reducer on A's to a reducer on B's. And people stared at this for a long time and related things, and they wrote some blog posts and talked to each other, and they concluded that that's a transducer. It's a Kleisli arrow in the list category, and that you can show by what we've talked about in this talk, or a variety of other related methods, that you can take that type and show it's exactly the same as that type. And there were a couple blog posts where they did this by different methods. So this stuff does come up, is that you do have in Clojure someone coming up with something like that, and they haven't given any types at all. And then we come along, we try to give it types and say, what the heck is that doing? And thanks to the power of reasoning we get from our types, and then, you know, throwing some abstract nonsense at it, we can turn it into a type that's much easier to get our hands on. And that's what we've done here. So that's another example of why you might care about this. So Yeah, I'm wrapping up about now, and as I say, just one more thing. Take some category C. Now look at things containing C but that have all the colimits. So something bigger than C to the extent it has all the colimits. And you want to take the initial thing, right? Something that has all the colimits, has the objects in C, and doesn't really have anything else, right? It doesn't have extra stuff. It's the tightest fit to add all the colimits to some category C. And as we see, colimits are super useful, right? We get naturals out of them, we get lists out of them, we get eithers out of them, get co-equalizers out of them, which we can't even talk about in Haskell. So if you want to have a really useful category, maybe you want to add all the colimits to it. So what's the most tight way we can add all the colimits to a category? That's for another talk, but that's one reason maybe that people care about Yoneda. Is one way to describe it is precisely the free universal co-completion of a category. And that's it. Thanks for bearing with me on all this. I find this fun. I hope you had some fun too. So, there you go.
Has the relation with the church encoding been made precise somewhere, or can we read about?
How's the relation with church encoding been precise? Probably. I've read things that have hinted at it. I can't think of like the paper to say that it's exactly about it.
Something that just gives the idea. Yeah.
Categorical approaches. I don't have a reference off the top of my head. Do you have an answer to that? Microphone. Oh, I turned it off. Yeah. Sorry. Sorry. I'll give the answer again. Has relations with church encodings been made precise? I don't know of anything that's been devoted just to doing that. I've seen church encoding studied categorically. I haven't seen someone do a back and forth. I don't know if you can do a full back and forth. That's why I was hand wavy about it. I'd like to see that.
Okay.
One paper you might look at is Ralph Hinzer's paper called Church Numerals Twice, which I don't think it explicitly goes through the co-limits, but it explains the church numerals and the connection. Yeah.
Could you take us through how the two types for the transducer are the same? Because I didn't understand that.
Oh boy.
Sorry.
That's why I had the links to the blog post. Off the top of my head, I don't think I can. If you think about, Jeremy can, if he wants to. I could give you the intuition for it, but he can give you the answer.
Well, I was just going to give you the intuition, but if you can do that, that's fine too.
No, I prefer yours.
So that transducer type, the right-hand pair of parentheses is redundant because of the association on the arrow. So you can, the type is, for all z, take a binary operation a to z to z, and a b, and a z, and give me a z. Now permute those arguments to take the b out of the front. It takes 3 arguments and gives you a z, so bring the b to the front. It takes a b and gives you an a to z to z to z to z.
Yeah,
that's the church encoding of lists. That's the type of fold R, which is the church encoding of lists. So transducer takes a B and gives you the church encoding of a list.
Yep, that's a great answer.
Hi, could you go back to the slide where you had this wow moment when you discovered the colimit of the lists?
Yeah.
Wow. And have you thought about how this relates to the free monoid?
To the free monoid? Not exactly, but it obviously sort of does, because you're looking at sort of, your dot as a monoid object where all the morphisms represent the different things. So I'm sure you can sort of do it that way. I was happy to find the frayed thing, and then I just sort of realized that you can do lists the same way. I don't know if that's been done that way in the literature. We usually do it the other way that I showed next. So.
Neat. More questions?
Hi, so I kind of just let the category theory waft over me, so I was just mainly looking at the types, and it seemed to me that so the types for the category, the calendar scheduler looked a lot like what you would A, feed into an unfold, and B, what you would get out of an unfold R.
The types of the what?
For the calendar scheduler.
Yeah, probably.
Yeah, and then also, similarly for the list and nat, they look very similar to the types you would get when you take the data constructors for lists and for the church encoding of natural numbers and turn them into F algebras. And I think it's kind of been touched on before, but I kind of wanted the next part of the answer, right, from the intuition to why this seems to happen so often, right?
So why does this happen so often? Gosh. I mean, sort of, it's sort of right. When you look at the way we define data types, as you said, initial algebras, right? And that's how we build data types in Haskell. Is, I mean, and we've got some type system extensions, so we can do some fancier things now that aren't quite initial algebras. And then we've got people who are writing papers on how to deal with that. But generally, we have initial algebra semantics for all of the core things we write in Haskell, and that means that it sort of induces exactly these things where you can go through and replace all the constructors with all the things you can do with the constructors, and that's how you move between the object and its so-called, quote, eliminators in a very mechanical way. And that's really just been built into the language, I think, from the get-go in some sense. That's in a way, my best answer there. I've been interested in looking at, and haven't gone back and found enough stuff, but right, so data structures with pattern matching and sort of the way that you could define this stuff only really came into functional language in the early 80s with Hope, I think, was the first language that had them, which was Burstall and Sinella. And it had come, apparently, there was some discussion in Landon earlier about it. But it came relatively late in the game, and people had figured out a fair amount of related stuff about, and they had to figure out when you introduce data structures, what are we going to do with them? What are the allowable things? And they sort of had, they started to work out the theory, in my sense, building in, maybe not with all the diagrams, but sort of these understandings in some sense to begin with. That's sort of the best answer I can give, and that there's a result I didn't talk about here that I can't explain fully, but it's related to the thing with the co-limit of a sequence, which is the fact that in Haskell, what we call data and codata, or initial and final encodings coincide, so that we can mix the finite things and the infinite things in interesting ways that some people would consider illegal. If you take the stuff I gave here and a bunch more thrown on top, then that's the way you can find that result. And that's one of the interesting features just about Haskell as a language, that we can mix the finite and the infinite descriptions of the list. So I think that must have something to do on some level with your question. That's the best answer I can give.
Okay, well, one final short question, perhaps? Okay. No,
All right.
thank you again.
Thanks, everyone.